theory of attraction and gravity, I postulated the entire concept of gravity is imbalance of charges caused by the Earth's electric field, which induces electrostatic and electromagnetic induction and attracts everything. I deduced the line of forces due to the Earth's electric field are accelerating everything toward the Earth's surface and to the center. In fact, the determining factor is not the force of gravity. It's the mass which is being accelerated, who dictates how much lines of forces I need to accelerate. In order to prove the theory of line of forces generated by the Earth's electric field, I incorporated the conservation of angular momentum with many experiments and compared to the nebula, dust, and gases for forming planets to the ice skater and my suspended objects in my science lab. To prove that the suspended objects with inertial masses are affected by the Earth's line of forces, which are accelerated by the Earth's rotation. As we know, the Earth is affected by the Moon and the Sun differential gravitational forces. Based on my 1960s observations, I replaced the Sun with the Earth and the Earth with the small suspended steel balls to measure the torque or angular acceleration of steel balls caused by the Earth's differential forces. Everything in our universe has a mass or inertia, which is the measure of the mass. Even the hydrogen atom electrons has inertia. The magnetic field cannot attract everything, but the Earth's electric field with its lines of forces can, which are also accelerated by the Earth's rotation. Gravity of attraction is caused by the Earth's electric field to make room by repelling the like charges and causing uneven distribution of charges in objects or separation of charges that attract them. Even in a molecular level, we can see the influence of inertia with less atomic mass. For instance, in gases, the hydrogen molecule H2 needs less lines of forces to accelerate compared to the oxygen molecule O2. In other words, less lines of forces are holding the hydrogen molecules. The average speed of the H2 at the room temperature is 6,400 kilometers per hour, compared to the O2, which is more massive, 16 times more, is only 1,600 kilometers per hour. Thank you. You can see this is a model of hydrogen atom, which was done by Niels Bohr in 1913, and in fact, this part was my idea. It was my imagination that I can draw this, and you can tell even the electrons have moment of inertia, or they have inertia. Well, of course, the spin was discovered by two Dutch physicists, George Uhlenbeck and Samuel Goudsmit. But Niels Bohr said that the electrons are orbiting the nucleus. They also discovered, beside that, they also have the spins. This experiment is about Albert Einstein's principle of equivalence. That means that gravitational mass and inertial masses are the same. So the reason why I'm doing this, I just wanted to demonstrate that how much less force you need to accelerate if something like this has an inertial mass. The reason why, this is 1 kilogram plus the weight of the wire, which is only 1.5 grams. So everything is suspended. So in other words, the ceiling, that hook on the ceiling, it is holding the entire weight. So we can just easily distinguish between gravitational mass, which is this one. See, this is exactly 1 kilogram or 1,000 grams. And if I want to do this against the force of gravity, look, see, I need exactly 1 kilogram to accelerate this. See, this is now not touching the ground. So if I have even 99 or 999 grams, I won't be able to accelerate this. You can see how much heavy that is. This is the gravitational mass. But this one is an inertial mass, and technically what it means, entire weight, if it's like 1 gram or 1,000 grams, is suspended or supported. It's just easy to demonstrate. See, this crystal ball is exactly 1,510 grams. And when I pick this up against the force of gravity, you see I can feel how much force I need to accelerate this upward or against the force of gravity. But once it's supported by the ground or the floor, you can see by the smallest force I can accelerate this. This is another one. This is a metal, and this is 1 kilogram. You can tell how little force I need to accelerate this. And this cylinder is 4,384 or 4.38 kilogram. You see how much less force I need? The reason why this entire weight, 4,038 gram, 4,384 grams is supported by the earth. But of course there is no doubt this has more friction, but see this ball doesn't have any friction. See how easy we can accelerate this. We can assume this like a 2,000 kilogram or like a SUV. If it's against the force of gravity, we want to pick this up, we need a hydraulic jack. But one ordinary person can move this back and forth if the tires are properly inflated. And in order to show you this, I had to do one experiment, and this is exactly 1 kilogram. And what I did, I had a small ball, it's exactly 1/3 of a gram. And imagine that 1/3 of a gram, by the force of gravity, can accelerate this exactly 5 millimeters. But if this were on the ground, there is no way that we can accelerate it. Even if it was like this, on the ground there is no way. But when it's suspended like this, wire, entire weight is supported by the wire. So what I did, I run this through this little pulley. It's very small pulley, and then you can tell when I let this go, force of gravity pulls this 1/3 of gram and then accelerate it almost like 5 millimeters. See that? Well, of course, if I increase the force, I have to be able to just make sure this is stationary, it's not moving. See that? This is another experiment, and this is electronic scale. It's very sensitive. Even if I move my hands against this, it's going to show their molecules are moving. See, you can tell 0.1. So in other words, I'm creating low pressure. When it's a low pressure like that, their molecules are less over here, so gravity is sensing less. So what I did here, I have a wood which is exactly 1.82 grams, and the wire itself is 1 gram, and the steel ball is exactly 73.2. And when I suspend this on this scale, it shows the 100%. Say 181.5, which is the same weight of the wood, wire, and the ball. Well, of course, this has to be stationary, it shouldn't be moving. Well, of course, I could get very expensive scales, goes to 100 of the gram, but I couldn't find any, and this one goes to 1/10 of the gram. And the entire idea is, when I did my experiment, always everything was suspended. So in other words, they had the inertial mass, because there is no way I could prove my theories by having something on the floor. Everything was suspended. Well, of course, this one has to be with wire, but the rest of my experiments are suspended by threads. This part of my experiment has to do with free fall, which I compared to my suspended bowling ball and the steel balls. And then I noticed something strange. When we're free falling like this, when the objects are free falling, you can tell I have the position, I have the fall time, 1 second, 2 seconds, 3 seconds, but you can tell here the velocity minus 9.8 meter per second, and this is the acceleration, which you can tell the second, the 1 second, 2 seconds is just double, triple. And then I noticed the same thing in my rotating balls. Well, of course, these have more resistance because of this wire. And when we have something like this, it's only the resistance of the air, and it depends on how aerodynamic the objects are. And then, in a minute, I show you or I demonstrate exactly what I mean by my rotating balls. In fact, this has to do with the Earth's gravitational force. And as we know, the sun and the moon are exerting force on Earth, and it's called the gravitational or differential gravitational force. And the same thing happened to my steel balls and the bowling ball here, which is suspended, but now I had to stop them, and then I can show you when they rotate. And in northern hemisphere, always when they're suspended like this with the inertial mass, they rotate counterclockwise. If I take this to the southern hemisphere, it'll be clockwise. This is a bowling ball, and it's exactly 15 pounds, or it's 6,780 grams. But I noticed something strange. In order to overcome the inertia, the steel ball like that, 16 grams, can rotate 1,000 RPM in 25 seconds. And this bowling ball, which is almost 8 inches across or 8 inches diameter, it takes 10 seconds for one rotation, and the second rotation is exactly 5 seconds. And I would say like 30 seconds, it takes only 6 rotations. And as they go smaller mass, like this one is 150 grams, and this one is like 96 grams, and amazingly, they never get 1,000 RPM. But that one, which is 16 grams, in 25 seconds goes 1,000 RPM, so I double the mass. The other one is exactly 32 grams. It takes 50 seconds to reach. Well, of course, 50 seconds to reach 1,000 RPM. I have this laser beam, or it's a tachometer, and it's very precise. It shows to 9,099 RPM, and it's very accurate. So when I get this, and then of course I have to have the reflective mark on the balls. I'll show you in a minute. When I get this against those balls, and then it shows exactly how many RPMs they go. See, when I release this now, you can tell exact weight, and this thread is like 2.5 grams. Exact weight is suspended, and you can tell. And this is just the plane. It shows how small this rotates. It takes exactly 10 seconds for the first rotation. Well, of course, I had to put a mark over here. You can tell how slow it goes. Oh, it's stuck. I have to do the other. I have to go one notch higher. I have to go here. See, you can tell this is the index, and then if I let this go, because it's extremely massive, it's going to go so slow. You can tell. When I get the time, it takes exactly 10 seconds for the first rotation, and most amazingly, the second rotation is exactly 5 seconds, and then kinetic energy comes in equation, and like the small balls, it rotates. Well, of course, there's something. In order to overcome the inertia, this is huge. And later I will explain it has to do with the conservation of the momentum. See how wide it is. This is 8 inches, and in fact these are like 1 inch, and the other one is less than half inches. So if I have a ceiling like maybe 100 feet or 200 feet, this will rotate forever. But see what happened, the Earth, as I explained, the line of forces or the flux lines which is emitted from the Earth, they're causing rotation on this, and also the Coriolis effects and the Earth's rotation causing this to go counterclockwise. But the important fact is, when it's massive like this, it's less acceleration. The less massive I get, like I said, the other one, I have even like 7 grams, it goes less than 16 seconds for 1000 RPM. So I have to stop this now. See? And then, since this goes counterclockwise, when I let this go, if it goes like 100 turns, exactly this will rotate 100 turns clockwise. And these two, one of them is 150 grams and the other one is 94. I'll let them go. You can see. But of course they have to be perfectly stationary. See? That 151 accelerate less. So in other words, it takes more time to overcome the inertia. But you can tell how fast that 94 is going. You can compare how fast that goes. But you can tell if you put a small plane like this, exactly like a pendulum, you can see how this one is. Exactly like a pendulum, they make like ovals. And the reason why, they are going with the Earth. And in fact, the Earth's rotation is causing them to deflect. And that is the direct consequences of the inertia. It's almost like a pendulum, but pendulum we can see, they make a huge ovals like this. And I remember when Mr. Foucault did, you could tell how big those ovals are, but this one is a little bit, now we can tell in a smaller one, this oval shape is more, we can notice more. Now I'm going to demonstrate what I mean when they go 1000 RPM. Because in fact we are assuming the line of forces here, or the force of gravity in my lab is exactly the same. This is only 1 meter, so it's not going to be a big deal, or it's not going to be changed. But overall, the line of forces are always affecting the suspended ball, because like I explained, 100% of the weight of this is suspended through this wire. If I put a scale over there, the electronic scale, it will show exactly 151 grams, which is this steel ball, plus the weight of this. And this ball is 16 grams. I have to let this go so you can tell that oval shape. So this is exactly 16 grams. And then I put a reflective mark here, and this is electronic counter, and it tells me exactly when I get the time, how long will it take for 1000 RPM. But you can tell how fast this one accelerates. I mean, the angular acceleration is amazing. Okay, so this is the laser beam. Let me turn this on. Well, of course, it's very difficult. I mean, there's no way we can get this 100%, but I do my best. We get the time. Okay. See, you can tell it's going back and forth a little bit, even though these are made in factory. I would say maybe they're sphere 100%. See, now I have 400, 537, 500. 800, 814, 835, 875, 900, 9. Sometimes I have to reset. 919, 912, 990. See, almost like 1000. So, if I do on this one, well, of course, I don't want to waste time. If I do on this one 32, because the mass is double, it's going to be exactly 50 seconds. But now you can tell, if this rotates 800 times, and then this has to go the opposite side, clockwise. Let me show you what I mean. See, when I let this go, now this should go clockwise. The reason why Earth's differential rotation is causing torque on this, and this torque is causing the thread or a string to go. Now you can see I let this go. See? And sometimes I'm doing a big warehouse in a tall